Welcome to our Senior Design 1 Robotic Delivery System presentation. I'm Brandon Bryan, I'm the project lead, and I'll be taking you through a brief summary of our work this semester. The objective was the creation of a delivery system using autonomous robots. Our team worked on the algorithm, which would be used to control the robots, while the map team worked on a pathfinding algorithm development. So if something like Google Maps already exists, why develop this? Well, Google Maps is not designed to work with robots. For example, if you're in Uptown Charlotte and you're using the walking algorithm in Google Maps, it will assume that you can traverse stairs. Our delivery robots cannot do that. Therefore, algorithm development for us becomes a little more nuanced and tricky. Also, the node resolution provided by Google Maps is sufficient for human use, but a robot needs more reassurance with higher resolution nodes. The specifications required that the algorithm be a derivative of Dijkstra's or A-star, generation of a campus map for the robots to use, and adding into the algorithm the existing accessibility ramp data for the robots to use. So our technical approach was to create a working Dijkstra, reduce the runtime of the algorithm by simplifying the path, import existing GPS data for the campus, visualizing this data to a potential user, maintaining resolution integrity through snapshots and stitching, then importing that data into Gazebo and ROS. This semester, we have created a working Dijkstra's algorithm. We have used an abstraction to decrease the runtime into the order of milliseconds, and we've implemented all of the buildings on the Epic side of campus. So we have successfully imported a campus map into a gazebo simulation. We have then visualized that data by taking our existing path data and superimposing it on top of the campus map. We have also created functions to modify the generated path. Looking at figure 4 on the left, a robot would have a much more difficult time navigating that path because there's too many gaps, so we increase the resolution of the nodes to what you see on the right. It's easy to see that a robot would have a much easier time navigating a path like that as opposed to the before on the left. The first challenge was overcame by abstracting the nodes and encapsulating many nodes like a street into one node, manually importing the GPS ramp data for use with the algorithm, using the interpolation function to add a higher resolution of nodes, and of course scaling the map appropriately for the simulation environment. So in the future, as we scale to a larger campus map, we want to keep the runtime in the order of milliseconds, begin testing the turtle bots on campus, and complete a user-friendly graphical user interface to be demonstrated. So other areas where the team's developments can be seen in the future are wheelchair accessible routes being added to programs like Google Maps, in navigator robot applications, and in surveillance and security robotics. Thank you very much. That concludes this presentation.